Alright, welcome back to another video. This is a bonus video. This will be a algebraic proof for the power rule, the derivative of x to the n that equals nx to the power of n minus 1. I will be proving this for whole numbers, positive whole numbers of n, so 0, 1, 2, 3, and on. And I will be using the binomial theorem. I won't be explaining exactly where that comes from, but I will be using it in the proof. So, well, let's do it. Well, we'll begin with the derivative, the definition of the derivative, and I'm going to actually just use a limit. Instead of delta x, which I used in the previous video, I will be using h because it's a more common notion. Right, so we'll have h approaching 0, that's just this part, the limit part. It's just a little bit more formal way of writing it. And then we'll have our fraction here, well, x plus h, that's the input, and we have to raise it to the nth power, and subtract out x to the n, and then we have to divide by h. There we go. Okay, and now we'll use the binomial theorem. The binomial theorem is a way to systematically expand things like this, where you have two terms added or subtracted or whatever raised to some n power, and you can do this with a plus b squared. That'll be a squared plus 2ab plus b, and you can do it for a plus b cubed. That'll be a lot of algebra, but you can do it kind of like this, but this takes way too long, especially for bigger powers of n. So to get around that, a formula was invented. I don't know by whom, but that doesn't matter. I'll just write it down. So this is a summation. When you have a summation, it just means you kind of add everything like this. So it will become clear once I implement it. Alright, so a special function is also used in the binomial theorem. It's called the choose function, and it's n choose I here. So that'll be a to the I and b to the n minus I. It doesn't matter if you don't fully understand what this is. It will be you don't need to know the details of this to understand the proof. Alright. Let's go back to the limit now. And let's use this thing we found to expand x plus h to the n. So, alright, the limit of h to 0. We need a little bit more space. There we go. I equals 0 up to n. Alright, and it's going to be, and then I have x to the I, h to the n minus I, and I still have to subtract off x to the n, obviously, and all over h. So now I'm going to expand this out, because this is kind of a summation. So I'll expand this now. Alright, so the first term that we're going to have is x to the n, that's just x to the n. That's for I equals n. Then I'll get n choose n, that's how that's pronounced, and that's just 1, always. And obviously h to the n minus n, that's going to be 1 also, because that's h to the 0, which is 1. Alright, and then I have to add the next term, which is going to be n minus 1, or n choose n minus 1, x to the n minus 1, h, and then blah 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 blah, until we just have h to the n, and then again I have to subtract off x to the n. Alright, so now already you may notice that, let's take a different color, this term will be subtracted off by this term, and that will leave us with 0. So let's just quickly do that. So we'll be left with, from this onwards, right? that's going to be n choose n minus 1 x like that. And I'll just do one more term to make it extra clear. Minus 2 squared on and on up to h to the n. And now you may notice that we're left only with terms that also contain an h, so we can actually just divide out. So we'll divide out by h, like that. And we're going to be left with this, something like this anyway. And every power of h will be, every exponent will be reduced by 1 since I divide by 1. So this is going to be 1, and the next term minus 3, that's going to be h squared all the way up to h n minus 1. And so now you may notice that all of these terms from here on out contain an h. So actually what we can say is, because we have a limit that h approaches 0, that we can just say that all of these terms all become 0, which just leaves us now with this, and already the exponent is correct, right? We know that's correct. We already saw that. But now the only thing we need to do is to find out, does this actually equal n, right? Well, to do that, we'll look at the definition of the choose function, and it involves something called the factorial. Now, the factorial is quite easy. It's just every number multiplied together up to n. So that's going to be 1 times 2 times 3 all the way to n. Alright, so the definition of the choose function, of if I just have n and k, then that'll be n factorial divided by k factorial n minus k factorial. So this is something from combinatorics and probability, but it's also used in something like this. Kind of fun. Alright, so let's now enter our two values that we got from the limit. So the first one is just going to be n factorial, the next one, that's n minus 1 factorial, and then I have n minus n plus 1 factorial. Now let's work this out. N minus 1 factorial, n minus n, that's just going to be 0, so we're left with 1 factorial. And now I'll quickly expand this so you can see what's going on. It's 1 times 2 times 3 all the way up to n. And here, just 1 factorial, by the way, that's just 1, obviously. So we can basically ignore this. And so this n minus 1, that's going to be 1 times 2 times 3 all the way up to n minus 1. And we can actually see that all of these terms, they all cross out except for this n. So we're just left with n, which completes the proof. Look at that. Very nice. So that is the derivative, the proof for the power rule for whole integer numbers, for whole and positive numbers for n. Since the binomial theorem that I used here, it doesn't really work for fractional or other numbers, other values of n. Alright, so thank you for watching, and I'll see you in the next part. Bye.